Over the past few videos, we've derived and defined criterion for identifying when a system reaches equilibrium. When we have an isolated system, so for constant n, v, and u, what we find is that when these systems reach a maximum in their entropy, they then reach equilibrium. And so for these types of systems, their entropy grows towards a maximum. For a constant NV temperature system, what we find is that it's not necessarily that the entropy of the system reaches a maximum, but rather that the Helmholtz energy reaches a minimum. So ASYS decreases towards a minimum. And so even for constant NVT system, even if the entropy of the system decreases, overall the entropy of the universe would reach a maximum. Okay, that's what we find. And then for a constant NPT system, we find it's the Gibbs energy. That reaches a minimum. And that's when the system would be at equilibrium. When things, where the properties would then just stay put. Okay? And so mathematically, we showed all these things. But now let's talk about like what this all physically means. Okay, so like physically, what does it mean? Or like why are our systems minimizing their Helmholtz or their Gibbs energy? Okay. All right, and so what we could do is we could actually just once again take a look at those defining equations for Helmholtz and Gibbs. So for the Helmholtz energy, for the system's Helmholtz energy, we see that it's internal energy minus T entropy. Okay? And so, for the Helmholtz energy to decrease, what must happen is that either U system must decrease, or, because of this negative sign here, and or S system must increase, right? And remember, we're looking for constant NVT systems, the temperature would be constant, right? So that's why I'm saying it's either this decreases or this increases, okay? All right, and so what we have to remember is that, you know, the internal energy of a system, that describes, you know, the sort of microscopic movements or the microscopic energy of the molecules. While entropy here is the number of ways you could arrange those molecules, or a number of ways that the molecules arrange themselves. Okay? Right? And so, if delta, or if the internal energy of the system is decreasing, right, so the system is losing energy, we know from the conservation of energy from the first law of thermodynamics that that energy needs to go somewhere, right? The overall energy needs to be conserved. And so if our system is losing internal energy, what ends up happening is that that energy goes into the reservoir. And that energy can either increase the internal energy of the reservoir, or it goes into increasing the entropy of the reservoir as well. And so that's why, in the end, even if the internal energy of the system is decreasing, that leads to an overall increase in the entropy of the universe. Okay? All right, and so that's why we see that for these constant NVT systems, the Helmholtz energy will decrease as the system goes towards equilibrium. We can make similar arguments for the constant NPT systems. Right? So if we look at the Gibbs energy, that's H minus Ts, right? Which we could split up the enthalpy term into internal energy plus PV system minus T system. Okay? All right, and so for the Gibbs energy to decrease, what we need to see happen is either the internal energy of the system and or the volume of the system decreases, and at the same time the entropy of the system would increase as well. Okay? And so any energy lost from the system would once again go into increasing the energy of the reservoir or increasing the entropy of the reservoir. And so overall, we would see a positive increase in the entropy of the universe.